Okay, guys. Not ideal, but I am going to be out for a little bit longer. I'm not sure exactly. I should be back at the very least for Thursday. We're going to keep moving along. The two things we were going to do anyway, we should be able to do through videos. So yeah, not ideal, but we'll make it work. So the plan today anyway was to go over the sound and waves assessment. I told you that that had to be finished. I was going to close it Friday night. I wound up just closing it now. It's about 8 o'clock on Sunday. So up until that point, if you took it, great. If you didn't, well, you now have a 0, and you better be talking to me as soon as you see me again because, well, frankly, you had 2.5 weeks. If you can't get that done, that's just kind of pathetic. So we're going to go over it. If you have any questions on this, you didn't understand an explanation, anything like that, you guys have the number to text me. You can email me. You can ask the sub to write down a note and send it to me, and I will be happy to address those specific concerns. If you don't understand something, I can, do another video, post it up on Canvas, whatever it is you need. So, if you are in first or second period, you should be 100% good to go after this. If you're in fourth or eighth, we are going to have to still do the notes I did with first and second on Friday. I hopefully we can do those on Thursday. Once I've done that with fourth and eighth, there will be a retest opportunity for this assignment, guys. It's going to be over spring break. It will be on Canvas. So that's going to be available to you. As far as curves go, because I know some of you guys are going to ask, I haven't had a full chance to look at all the grades for this test yet. My expectation is these were AP questions. There will be an AP curve on it, so I will get that into the grade book early this week. All right. So with no further ado, let's start going through these. So question one, we've got a wave pattern. It's produced by a string fixed at both ends. Speed of the waves in the string is 4 meters per second. What is the frequency of the standing wave? So this part should be relatively straightforward. We're just going to use your basic equation for waves. So we've got V equals F lambda. Now, they tell you the velocity is 4 meters per second. It asks for the frequency, so we're looking for F. So that means we have to know lambda. So what you got to do is actually take a look at this chart here. Remember, one wavelength is one complete cycle. So starting at equilibrium, it's at equilibrium to a maximum, back to equilibrium to a minimum, and back to where you started. So, one complete path, all the way up, all the way down, and back to where you started. We're at equilibrium, max, equilibrium, min, equilibrium. And you could go the other way along this. It really doesn't matter. But that is two complete wavelengths. So our wavelength here, if two wavelengths is 1 full meter, then one wavelength is half a meter. And so the end result is 4 divided by half, which is the same as 4 times 2. Should be 8 meters per, or 8 hertz, which is appearing as an option right. Okay. So, quick announcement with this. Someone first period did let me know there was an issue with this question. There was not a correct answer. The answer should be 8 hertz. If you started the test before I changed that, which was at like 9 o'clock the first day it was available, so it shouldn't be an issue for the vast majority of you, considering how few of you were even done with the first love at that point. But if you think you had that issue where you couldn't see the correct answer because you started it too early, let me know. I can go ahead and fix that for you. Not a big deal. So, like I said, it shouldn't be an issue for the vast majority of you, but it could be. All right, question 2. What happens to the wavelength of a sound if the frequency is doubled? Okay, so we're dealing with wavelength and we're dealing with frequency. So it sounds like we're again dealing with V equals F lambda. The trick here is it says of a sound wave. And the reason why that's important is sound waves travel at 340 or 343 meters per second. So V is constant, can't change. That's 343. So if we double the frequency, if we make the frequency twice as big, then what do you have to do with lambda? Because I'm writing this really weird. Basically what I'm saying is you're making this, let's ignore what I just wrote here. This is constant, right? So this must be 2 times bigger. If V can't change, well, the right side of the equation can't change. So if this has gone up by 2, this must go down by 2. So if the frequency is doubled, what happens to the wavelength? It halves and the speed halves. Well, no, because the speed must stay the same. Can't be an option. Speed doubles. Nope, can't be an option. Okay, so we only have these two as options. And we said if the frequency doubles, the wavelength must be twice as small, so it would be halves and the speed remains unchanged. So number 3, we got 2 wave pulses and they both hit point X at exactly the same time. They're traveling in opposite directions towards each other. What direction will the string at point X move as the waves go past each other? Okay. So remember, this is the superposition principle. And what the superposition principle says is if I've got 2 waves, in fact, let me pause this and pull up a good. Okay, so this is the superposition principle. Basically, if I have 2 waves here, so I've got this one going peak, down, peak, down, peak, down. This one peak, down, peak, down, peak, down. Now if you notice, we've got a wavelength starting here, up, down, back to equilibrium. This is one wavelength right here. Up, down, back to equilibrium. This is one wavelength right here. So if you notice, there's a peak where a peak is, there's a trough where a trough is, or minimum where a minimum is, whatever you want to call it. So if you take this amplitude here and this amplitude here and you add them together, what you're going to get is roughly double the amplitude. Minimum, minimum, line up, we get a very big minimum. Over here we've got a peak, so let's say this is some amplitude A, and this is an amplitude A. That's a terrible A, but you get the idea. So this has a wave, an amplitude of 2A. Tell you what, let's change the color really quick. Okay, so over here we have this wave, amplitude of A, and over here this has an amplitude of negative A, which adds up to 0, so you have no wave. Amplitude of negative A plus amplitude of A gives you an amplitude of 0. A plus negative A, 0. Negative A plus A, 0. You get the idea. So superposition principle, you add up their amplitudes and this is the resultant. This, by the way, constructive interference. This is destructive interference. Now, to give you a slightly better idea, this is going to be hard to see. Let's see if I can zoom in on this a little bit and make this work. Let's give that a shot. There we go. Okay, so I've got 2 functions here. Now, you don't have to understand how to do the math of this. It really doesn't matter. If you're taking college algebra or whatever it is they call it there, you'll know that this number in front is essentially what's called the phase difference. It's really not that important. What's important is that you notice, like along this line, we have a minimum here, and if we keep going down this line, we have a minimum right there. Those 2 minimums add together, you get a much taller wave. You start shifting it, so all I'm going to do is I'm going to move this wave over to the right a little bit. So let's say I make this 1. I change that. So now, oh, actually, I'm sorry, I've just changed the amplitude. Give me one second. Okay, so I'm not going to do, sorry, that's that number in front's the amplitude. The phase difference is over here. Anyway, so if I make this 0, notice now this wave has an amplitude of 0. The resultant and this match up. If I flip that top wave, so its amplitude is the exact same side but opposite as my second, I have a minimum right here along this line, and if I follow that down, that lines up with a peak, and I've got nothing. So that's what we mean by the superposition principle. Now, what all that has to do with this particular question. It says both these pulses meet at point X. So again, let's say this has an amplitude of A, this has an amplitude of negative A. It might not be exactly that, but we're just making an approximation because all it's asking us is the general movement. When these both reach point X, this wave, the front of this wave, has an amplitude of A. So we'll say the first part, when they first start passing. This has an amplitude of A plus the amplitude of the wave at this point is 0. It's not going anywhere. So that means the pulse is going to look like the front of this wave plus nothing. It's going to be tall. So point X is going to start out by moving up. As the wave pulses pass, however, this one starts going lower. So if this was just this left pulse, it would start high and go low until it's back down to 0. This would start at 0 and go down. So this is going down, this is going down even more, and so it's going to start going down. As they pass, or as they reach the end, this has an amplitude of 0, this has an amplitude of negative A, and so it's going to be down to negative A. So it's going to start out by jumping up to the top of this first wave, and then because this goes lower, because this is going lower, it's going to drop down to negative A. It's going to go up, then down. Question 4. Alright, so for this question, number 4, vibrating fork makes sound waves that travel in the air around it, and the amount of time the fork travels to make one complete vibration, the emitted wave travels. Well, so basically, what you've got here is V equals F lambda. So let me get my pen out here. So V equals F lambda. In the time it takes to make one vibration. So if your frequency is 1, what is your velocity? Well, it's lambda. So the answer should be about 1 wavelength. Basically, the definition is one vibration creates one wavelength that moves away. The next vibration creates the next wavelength that moves away. Not a whole lot to it. Number 5. 2 answers are correct. For correct, you must select both correct answers. The Doppler effect has multiple factors that affect the frequency heard. Of those factors, which are the 2 listed below? Literally all it is the speed of the source and the speed of the observer. That's it. How loud the sound is not going to affect the frequency, just how loud you hear the frequency. The velocity of the air is not going to affect anything because it's affecting both the observer and the source. Okay? So, quick clarification on the Doppler. So, the whole idea of the Doppler effect is if I've got some object, okay, that object is going to be emitting sound at some frequency. And so you can see the distance between one wave front and the next is pretty constant. So it emits a wave, it emits another wave, it emits another wave. All of these waves are moving away at the same speed, and so it moves out in a nice circular pattern. If, however, this object is moving, then it's going to emit a wave. Let me just restart this so it doesn't move. If the object's moving, it's going to emit a wave. But by the time it emits the next one, it will have moved, say to the right, closer. So on this side, because it's keeping up with the waves it's emitting, these waves are going to be compressed. Because it's moving away from the waves behind it, these waves are going to be extended. So what you're going to see is compressed waves here, bigger waves here. All sound travels at 343 meters per second. So if the velocity is the same and we have a shorter wavelength, higher frequency. Longer wavelength, lower frequency. And if this thing were to move fast enough, you see that the plane is actually moving faster than the sound emitted. That's supersonic. You know why you hear a sonic boom? Imagine all those sound waves hitting you all at once, all stacking up. That's what a sonic boom is. It's being hit by every sound that plane has emitted all at the same time. That air pressure all at the same time. And the faster you go, the more extreme it is. That's 2.5 times the speed of sound, which there's no planes that can travel that fast. But so that's Doppler effect. That's all it is to it. So the compression, you've got the expansion, higher frequency, lower frequency. If I was moving in this to the left, that's going to cause some impact as well, but not nearly as significant. But that's why you're going to hear things. Okay, so that's totally not what I meant to hit. But okay, so basically you got the idea of as it passed, you heard that drop in frequency. Okay. Question 6, exact same idea. At which of the points will you hear the greatest frequency? You're going to hear the greatest frequency where there is the shortest wavelength, which is going to be at point C. So for 7 and 8. Number 7, what is the amplitude of the wave? Well, remember, the amplitude is from equilibrium to your max or from equilibrium to your min. It is not min to max. So this is just, can you read a wave? And it's 4 centimeters. Done. Question 8, what is the speed of the wave? Well, that's a little bit trickier. They tell you the period of the wave is 2 seconds. Okay? So what that means, remember, is that it takes the wave 0.2 seconds to move, to complete one cycle. So what you need to do is we have V equals F lambda, right? And I also gave you on the front of the quiz, F is the inverse of period. So 1 over 0.2 is 1. This has a frequency of 1. So we're looking for velocity. We know the frequency. We need the wavelength. Well, equilibrium to max, to equilibrium, to min, and back to where we started. This is half a wavelength and is 5 centimeters, so one complete wavelength must be 10 centimeters. So your velocity is 10 centimeters per second. Actually, you know what helps is if your teacher's not an idiot. Let's try that one more time. So, yeah, it turns out 1 divided, or frequency is 1 over period. Turns out 1 divided by 0.2 is never 1. It should be 5. So V equals F lambda, your frequency is actually 5, your wavelength is 10, which is why the answer for number 8 should be 50, not 10. So 1 divided by 0.2. Good to know. Number 9. Fisherman notices that the wave crest passes through the bow of his anchored boat every 5 seconds. He measures the distance between 2 crests to be 7.6 meters. How fast are the waves traveling? Okay, so the numbers these are specific to you. Everyone's going to get a different set of numbers, but the process is the same. It's understanding that if the crests pass every 5 seconds, then the period of the wave is 5 seconds. So if the period of the wave is 5 seconds, then that means your frequency is 1 over your period. So with these particular numbers, it's 0.2. And then V equals F lambda. So in this case, 7.6 times 0.2, which is going to be like, I don't know, some number that I don't trust myself to add. Now, there is another way to do this that actually involves ignoring waves altogether. You know the distance between two crests is 7.6 meters. And you go from crest to crest in 5 seconds. Well, you're looking for velocity, which is in meters per second, right? Meters per second. It'll give you the exact same answer, because that's basically what we've done. 7.6, sorry, that should be a 6, 7.6 times 1 divided by 5, which is 0.2. Either way, we'll do it. Number 10. What kind of waves have the material move perpendicular to the direction of energy travel? So remember, for this one, there are two different types of waves. There are transverse waves. So if I have person A standing over here, and I have person B standing over here, energy is going to go from A to B. Now, if I have them do that by pushing something back and forth this way, like say a slinky along the ground, pushing it back and forth, then that's what's called a longitudinal wave. The material is moving left and right, and the energy is moving to the right. It's in the same direction. If they're moving perpendicular, though, the object is moving up and down, and the energy is traveling to the right. That's a transverse wave. So it's just, do you understand the definition of a transverse wave? Number 11, if the guitar string has a fundamental frequency of 684 hertz, what is the frequency of the third harp? Okay, so this involves going back to understanding fundamental frequency. So the idea is, if I have a string, that string has to be tied on both ends, right? Like a guitar string, piano string, something like that. So if it's tied on both ends, there must be a node, a point of minimum motion on both ends. Because if one end was just flailing around, that's not a very good guitar string. So the very, very longest wavelength, and remember, longest wavelength means shortest frequency, lowest frequency that you can have that has a node on each end is half a wavelength. So remember, nodes and antinodes, if I draw a wave, that's a terrible wave, but whatever. We have nodes at equilibrium, so node, 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 and we'll call that a node. So those are points where if I take that spring and I shake it back and forth, you can basically reach out your hand, grab a node, and it's not going to affect anything. Whereas the maximum points, antinodes, are places with the most disturbances. Okay? So when dealing with a string, you need a node on both ends because it's tied at both ends. Well then, so this is whatever wavelength that gives you 684 hertz. Well, the next wavelength that will give us two nodes on both ends would be node to antinode to node to antinode to node, also known as one wavelength. Well, if we've gone from half a wavelength to one wavelength, if we've doubled our wavelength, we've doubled our frequency. Okay, well, we're looking for the third harmonic. So we want something longer than a wavelength that'll give us three nodes, or give us a node on each end. So node to antinode, to antinode, to node, to antinode, and now we're back. So we have a node on each end. And if you notice, this part's a wavelength, this part's half, so this is 1.5 wavelengths. Well, basically, 1.5 wavelengths, let's actually make that look like a lambda, is 3 times more than this. So your frequency should be 3 times more. Literally, your frequency times the harmonic number. So frequency times 3. In this case, I was given a frequency of 684, so it would be 684 times 3 would be my answer. Number 12. Heike determines the length of a lake by listening for the echo of her shout reflected by the cliff at the far end of the lake. she hears the echo 2 seconds after shouting. Estimate the length of the lake. This is one of those questions that people think of how to do it and then they want to slap themselves. So, look, if it takes 2 seconds to hear the echo, that means your sound has traveled to the end, to the cliff, and back. So if it takes 2 seconds to go there and back, it takes 1 second to go from you to the cliff, and it's sound, right? And sound travels at a velocity of 343. This isn't even sound and waves, it's kinematics if you remember the speed of sound. So I think I said to use 340. If whichever you used, you'll be fine. But literally, it's just the speed of sound 343 times the time they give you cut in half, because you only need to go one way. So in this case, it would be 343 meters, or 340 meters. Question 13. Oh, this was a good one. I like this one. Okay. So for question 13, what is the wavelength of the string? Well, if you take a look at it, we have, equilibrium to equilibrium to, up, down, back, or down, up, back, doesn't matter. Up, down, back, or down, up, back, doesn't matter. Look, this is two wavelengths. So if two wavelengths are 1.2 meters, one wavelength is exactly half of that, 0.6. Number 14. What is the speed of the waves? Okay, well, then this gets back to v equals f lambda, because the wavelength is, we said the wavelength is 0.6, and the frequency, so that's lambda, the frequency is given in the problem as 120. So basically v equals f lambda means it's 0.6 times 120. Now, I just realized something as I'm going through this. You cannot get 14 right without getting 13 correct. So what I will have to do is go through, and if you got 14 wrong, I'm going to have to make sure you didn't do. So like, let's say you said your answer for 13 was 1, and then you said your answer for 14 is 120. Technically that's correct because you used your answer for 14 correctly in 14. So if you think that's you, let me know. But I'll try to do my best to go through and actually go find that. If an antinode on the string moves a total distance up and down of 4 centimeters, what is the amplitude of wave? So basically what it's saying is this is an antinode here. It moves a total distance up and down of 4 centimeters. Well, the amplitude is distance from equilibrium to max or from equilibrium to min. So if max to min is 4, your amplitude is 2 centimeters. Number 16 and number 17. So I definitely reworded this. You don't know voltage. You don't know what it is. You're not going to know what it is until after spring break. It doesn't matter. This is a graph. It is a graph that looks like a wave. You know how to deal with that. So, for number 16, the frequency of the tuning fork is approximately. Well, here's the thing. Number 1, look at units. 2 of these answers are in seconds. 2 of them are in hertz. Seconds is period. Hertz is frequency. You got a 50-50 shot just by looking at the units. But otherwise, remember, frequency is the inverse of period. And period is the length of time it takes for one complete cycle. So it could be equilibrium, up, down, back, or peak, down, and peak. So right here is about 0.004 seconds. 1 divided by 0.004 gives you 250 hertz. It's just about reading the graph. You don't care what voltage is. You don't care about any of that. 17. In order to calculate the speed of sound from the graph, you would also need to know. Well, we just figured out the frequency, right? V equals f lambda. So if you want to find V, you know f, you just need lambda. Wavelength. That's it. We've never, I don't think we, in any of your readings, we ever talked about pitch. Volume, who cares? We've never dealt into it. And you already knew frequency because you figured that out in question 16. Number 18 and 19. We've got a string. That's one wavelength. Up, down, back. So wavelength is 2 meters. Frequency is 5 hertz. The speed of which the waves propagate on the string, propagate's a big word, but basically you're looking for velocity. You know V equals F lambda. 5 times 2. It's 10. The fundamental frequency of vibration of the string is, well, that gets back to what we were talking about. This is one full wavelength. The shortest or smallest frequency, the fundamental frequency you can have, is node and node. Okay, let's actually draw that on the screen so you don't have to follow the mouse. So yeah, because the wavelength is 2 meters and we're dealing with node, I was going to draw it, but now I apparently can't. If your frequency is 5, then basically your fundamental frequency is going to be half that. This is the second harmonic. Fundamental frequency is the first harmonic. So if this is 5, it should be 2.5 hertz. Finally, question 20, and this gets back to superposition. So you've got two pulses moving at each other. Which of the following, and I just realized how crappy these pictures are, so we'll take a look at what's going on. So this should have just been one pulse straight up, B is blank, C is kind of the staircase thing, and then D is just this right here. Yeah, this is not very well done, so maybe I'll just drop this question. I don't know. We'll see how people did. But basically, what happens when they form, when they meet? Well, we've got, let's call this height amplitude A. This is A and negative A. So when these overlap, you're going to, on the left side, you have A plus A, which should be 2A. On the right, you have A plus negative A, so it should just be one tall column, should be A. All right. Now, what you're going to be finishing for the rest of today and what we're going to be going over tomorrow is, I said we're going to get back into rotational kinematics and torque. So again, 4th, 8th period, we will do the sound notes that 1st, 2nd did as soon as I get back for, good this time, for realsies, if you will. But we're going to do that when we get back. So we're going to move back into what were we doing before I left. So if you remember, we dealt with two different topics. We dealt with rotational kinematics, and we were dealing with rotational statics and torque. So you've got some homework tonight that I'm going to try and give you about 10 minutes to start working on. So don't forget we have these three equations over here. So omega equals omega naught plus alpha t. Remember, omega is rotational velocity. Alpha is rotational acceleration, and theta is rotational displacement. So this is, you got your translational versions, your linear versions, v equals v naught plus at. That's the same as omega equals omega naught plus alpha t. And final rotational velocity, or final angular velocity, is equal to your initial angular velocity plus your angular acceleration times t. So they're exactly the same. The trick is the conversions. So you've got to remember that if I give you something in degrees, and you need to change that into radians, and to go from degrees to radians, you multiply by pi over 180. If I give you something in rotations, you need to convert that into radians. And to convert rotations into radians, well, basically one rotation is 2 pi radians. So you multiply by 2 pi. To convert from rotations, oh, and by the way, if you need to go backwards, so if you've got radians and you need rotations, instead of multiplying by 2 pi, you divide. So if you are going from rotations to radians, you multiply. If you're going from radians to rotations, you divide. Okay, if you're going from rotations per second 2 radians per second, well, to go from rotations to radians, you multiply by 2 pi. To go from minutes to seconds, you divide by 60. Okay? So those are the conversions. I've got some very basic problems. You're going to get the answers, and I'm going to go over the solutions tomorrow in another video, assuming I am not back tomorrow. I'm not 100% counting on it now, but I'm going to do my best. The other thing we have is torque. Okay, so going through here, remember torque is this force times lever arm. Okay, so from where we're rotating to where we're applying the force, that's your lever arm distance or your radius, that's R, and then the force that you're applying. And we can do problems like this, or do problems involving rotational equilibrium or rotational statics. So remember we did this bear problem where you've got these two forces don't matter because they're at the point of rotation, so who cares? We do have the force of gravity of the bear, the force of gravity of the beam, and remember that force acts at the center of mass. We've got the force of gravity of the basket. We have the tension of the cable. These three forces of gravity are all trying to rotate you clockwise, so that's a negative direction. The cable is trying to rotate you counterclockwise, which is positive. The trick is the cable is at an angle. So what you have to do is the forces or the torques counterclockwise are going to equal the torques clockwise. That's what equilibrium means. Your lefts equal your rights, your counterclockwise equal your clockwise. So torque is F times R. Because this is at an angle, it's 60 degrees. We have to add that sine 60, so FR sine 60. And then all these are just F times R. So mg times R, mg times R, mg times R. The mass of the basket is 700. This whole beam is how many long? 6 meters long. So we've got the 700 Newton bear. It's 1 meter out. 700 times 1. Force of gravity times distance from rotation. The beam is 6 meters long, so we say its force of gravity is at 3 meters. Has a weight of 200. 200 times your distance from rotation gives you your torque. The basket has a weight of 60 newtons. It's 6 meters out, so it's 6. You plug it all in, you get an answer. Okay? So that's the very quick overview. Hopefully that kind of tickles your memory a little bit. You should have 5 or 6 minutes now to work on the worksheet once it gets passed out. Like I said, it's very basic. Just do you understand the fundamentals? We're going to go over it tomorrow, and then we're going to start talking about rotational inertia, the moment of inertia, and Newton's second law in angular motion. Okay?